All right, so now we're going to be talking about our decay models. And again, it's really the same form as our growth models. The only difference is that K coefficient is going to be negative. So that's where the decay comes from. So our decay model here is A equals A naught times E raised to the exponent negative 0.000121 times T. So that decay model describes the amount of carbon-14 present after T years. So we're back to years instead of seconds. And we're looking at the amount of carbon-14. Use this model to solve the following problems. Okay, so looking at number 4, if there were originally 20 pounds of carbon-14 present, so let's say A naught equals 20, that's our original amount. How much will be present in 10,000 years? So T equals 10,000. So we know A naught, we know T. We're looking for the accumulated amount, which in this case will be less than our initial amount of 20. So we're decaying. We're going to start with 20 and we're going to dwindle down to a smaller amount. All right, so let's fill in what we know, solve for what we don't. We have A equals 20 for our initial amount times E to the power negative 0.000121 times 10,000. And we just need to type that into our calculator, and that will give us our accumulated amount. And remember, we're going to round to the nearest whole number, so those are just our instructions. It's not printed, but that's just what we're going to do. So you would follow whatever instructions you're given, of course. So 20 times E. Remember, we're using that second and ln, second, and then the ln key to access E. And then I'm going to use my negative sign, so E raised to the power negative 0.000121 multiplied by 10,000. I'm going to type that all in the exponent. And if I'm rounding to the nearest whole number, that's approximately 6 pounds. Remember, my initial units were in pounds. So this is approximately 6 pounds. All right, so number 5, find the half-life of carbon-14. And you'll see this a lot in these decay models. Find the half-life of carbon-14, that is, how many years. So we'll be looking for a time period. Sorry, that question mark was so crazy. I'll try that again. Question mark, a little better. How many years does it take for only half of the original amount to be present? So there are a couple of ways that you could set this up. One is, let's play pretend. So if we wanted to use the pounds unit from number 4, let's just suppose. Okay, so let's suppose that initially we start off with 100 pounds of carbon-14. So when we're finding the half-life, after that many years passes, that means the capital A, the accumulated amount, should decay down to 50, half as much, right? So let's just use these as pretend numbers, and let's set up our equation. So 50 for our accumulated amount, 100 for our initial amount, E, and then to the negative 0.000121 T. Okay, so remember, we're just making up these numbers. You could have 200 and 100, you could have 2 and 1, anything where your initial amount then becomes half of that for the accumulated amount. All right, so solving this, notice that what I'm solving for, my exponent, has what I'm solving for. So T is up in the exponent. So I'm going to use that method where I isolate my exponential first, and then I take the natural log of both sides. And that'll get the T out of the exponent, so then I can work with it. So first I'm going to isolate, divide both sides by 100. 50 divided by 100 is 0.5. Okay, and now I can go ahead and take the natural log of both sides. Remember that allows us to use our power rule. So this gives me ln of 0.5 equals negative 0.000121 t times the natural log of e, which is just times 1. So it's really times the natural log of e, but I know that that's equal to 1, so basically that goes bye-bye. All right, and then from here to solve for t, I just want to divide by that coefficient, 0.000121, negative 0.000121. I'm going to divide by that on both sides, and that should give me t. So natural log of 0.5, scoot out of there, divided by negative 0.000121. And if I'm rounding to the nearest whole number, this is approximately 5,728 years. Now, I just want to point out, I set this up in kind of a funky way, but I got to the right answer. The proper way to set this up, the kind of mathy way, would be whatever your initial amount is, A naught, A would then equal half of A naught, right? 0.5 times A naught. So the formal way to set this up would have been, for my accumulated amount, half of A naught would equal A naught times e raised to the power negative 0.000121 t. And then I'm solving for t in the exponent. So first I would want to isolate, so I could divide out A naught. I don't know what it is, but it doesn't matter because it divides out. And then I'm still left with 0.5 equals e to the power negative 0.000121 t. So we end up in the same spot, take the natural log, yada, yada. So I just want to point out that that's kind of the formal way to get to that 0.5. But if you want to use regular numbers, if that helps you kind of get a grasp of it, that's fine too.